Thank you, and good morning. My name is Paul Shih. I am a signal supervisor with BNSF Railways. With me here today is Mark Aston from LB Foster Europe. Today, we'll be talking about a slide fence system that LB Foster and BNSF developed in 2018 using commercial off-the-shelf or COTS LiDAR technology. As many of you know, the implementation of microprocessor-based systems for use in safety critical applications is governed by the Code of Federal Regulations 236 subpart H. So this presentation will cover the concept of operations of the LiDAR slide fence system, the safety process that the design team used to navigate through the subpart H requirements from a COTS approach, the challenges that the design team encountered during this journey, and we'll wrap it up with a quick overview on parallels that our team at LB Foster have identified as common to both the North American and European safety regulations that are conducive to a potential cross-acceptance. Before we begin, I do want to say that this presentation does not imply BNSF's recommendation for use. Furthermore, it discusses the potential approach for analyzing data for this device and use case only. So with that, welcome aboard and we'll get started. For any new technology to be viable, it has to be at least as good, if not better, than the existing. So before we dive into a LiDAR slide fence system, let's talk about the existing slide fence technology. So shown here on the bottom left-hand side of the slide is a traditional wire slide fence. It is composed of line wires that are strung end-to-end, mounted on wooden posts, and positioned between the hazard and the train tracks. The line wires themselves are fed via a power source and monitored by an external relay. As it is a series circuit, if the circuit detects an open from a wire is breaking due to an external force, such as a rock, the relay de-energizes and sends a contact closure to the train control systems. So while this design is fail-safe and on a closed loop principle, it is very highly susceptible to false alarms. In a review of slide fence activations from 2006 to 2018, we actually found that the slide fence for one particular subdivision was only 4% accurate. So the false alarms are of an operational concern and of a safety concern. From an operations perspective, this is delaying trains that need not to be delayed. The less false alarms we have, the more fluid our network is. But from a safety perspective, each false alarm represents a maintainer or a crew member that we're sending out needlessly for an alarm that had no danger to train operations. And on the transportation perspective too, each false alarm only builds complacency and doubt in our system. For a system that works only 4%, I know I will have tremendous doubts if it indicates to me. So from this, BNSF Signal R&D was tasked to come up with a slide fence system that first and foremost was not as susceptible to false alarms, so anything better than 4%, right? And then second, something that could be easily restored. On a traditional wire slide fence, any slide fence activation requires track and time to repair. So we wanted something that if it was activated, could be easily restored if it was determined that it had posed no hazard to train operations. And on the other side of the Atlantic, LB Foster had been installing LiDAR systems at level grade crossings in the UK since 2013. They use it for pedestrian detection. So the idea was brought forth that, well, if these systems can detect the width of a person's legs, maybe it can also detect the width of a rock that is capable of derailing a train. So from this discussion came forth the LiDAR slide fence system. So this is the LiDAR slide fence that was installed about 30 minutes just east of Portland, out there along the Columbia River Gorge. Beautiful area out there. The scanners are mounted roughly around every 60 feet on existing wooden poles that already hold the wire slide fence. Each scanner monitors about 120 feet, so we're looking at 60 feet on either side of the scanner. And it's mounted about 2 feet top of rail, so it is imposing a vertical, say a horizontal detection plane above the top of rail. We have redundancy across the entire slide fence system, so every single area of track is constantly monitored by 2 scanners, such that if one scanner detects an intrusion, it will send an alarm to our controller. And all 10 scanners talk to a vital logic controller, and that is what we use to process the alarms and indicate to the train control systems. Again, redundancy is maintained along the entirety of the slide fence. So the last 2 scanners are configured so that it's only monitoring half of what the other scanners are. So the 60 feet that it is sharing with its adjacent scanner. Each scanner is also housed in a metallic shroud just to protect the scanner from damage from kicking rock or debris. And it also has a motorized shutter that is raised when a train is passing through the area. So they say seeing is believing, and that is very true. That is why our first test site for this LiDAR slide fence was developed in an area where we already had an existing slide fence. We had camera systems set up to capture a rockfall event, and our controllers were wired together so that we would be able to determine if the LiDAR slide fence had activated when the wireless slide fence activated and vice versa. Well, after we constructed the site and started digging into our numbers for historical slide fence activations, we found that for a test site of our size, we will only expect to see 1 to 2 rocks every 10 years. So decided, but probably wasn't the most productive use of anybody's time to wait 10 years for a single rock to drop. Well, if you can't see it, what's the next best thing? For us, that's the safety process. So as a CAUTS integrator, your safety process will revolve around 2 items. The first one being the PSP. That is the bread and butter of the subpart H process. That is spelled in 236.907. It lists 20 or so items that your product safety plan must address. But along with that is your RSPP, so your Railroad Safety Program Plan. That is spelled in 236-903. Every railroad has an RSPP on file, and whatever, as a COTS integrator, whatever you end up designing has to meet both the PSP and the RSPP requirements. The RSPP more or less shows how the specific railroad addresses each requirement of the PSP. One of the challenges that we faced when we were going through the subpart H regulations was that we found the regulations did not necessarily list them in an order that one would traditionally do a safety process. So this slide shows the safety process that our network control system teams have utilized in the past for their safety assessments, and that was something that our Signal R&D group adopted when we were analyzing our LiDAR slide fence system. For example, hazard log is listed as step number 7, but it is coming after your safety requirements section, which is listed in step number 5 of your PSP regulations. Well, in our case, your safety requirements are driven by the hazard log. The hazard log is created very, very early on when you develop your initial hazards and you start tracking them. You start working out the traceability from the time your hazards are identified to when they're mitigated, and your safety requirements come as a result of all those mitigations that you have done via the hazard log. As a COTS integrator and end user of a COTS equipment, your biggest challenge will be the VMV side. So what do I mean by VMV? VMV stands for verification and validation. Quite simply put, how we define it to be is verification, meaning did you build the correct product correctly, and validation meaning was the correct product built. The biggest issue that we experienced in our design of our LiDAR slide fence was on the software side regarding the VMV activities for the LiDAR scanner. Our manufacturer was based out of Japan. All their documentation was in Japanese. None of us on the design team was fluent enough or even fluent at all to decipher what any of those documentation meant. And the information that we were able to get were very, very limited in nature. And it's understandable. Companies have trade secrets they need to protect, and we understand that. But there are also ways to address those issues. For our case, you need to document your assumptions. So we recognize that we couldn't ascertain the software failure rate. So we use human performance to estimate the software rate failure. They were able to provide us with the number of levels of independent code review that occurred, and through that we were able to estimate a fairly conservative value for software. Of course, you would have to perform sensitivity testing to make sure that that estimation is appropriate. But in either case, the biggest thing to glean from this experience is that as you're working through the subpart H requirements, there will be things that will be hard to address or you might not even meet, but that is okay as long it is there to get the idea started talking about mitigations or alternate methods that can be used to address those shortcomings. Risk assessment is the meat and potatoes of the safety process. From a cost perspective, there are three main parts that you must consider. The first one is the basic requirement, and that is spelled out in 236-909, and that is your minimum performance standard per subpart H. A basic summary of it is that your mean time to hazardous event of the proposed system must be greater than or equal to the mean time to hazardous event of the existing system. And that goes for about anything, right? For any new technology, as stated previously, for it to be viable, it must be at least as good, if not better, than the existing. In order to determine these mean time to hazardous event values, fault trees are your friends. In this case, there are two fault trees that at a minimum you will need to make. The first is the functional fault tree. The functional fault tree will allow you to determine the minimum safety level that the existing system is at. And that will become the basis for your new system based off of the COTS equipment. After you conducted all your design, your V&V activities, you will then rebuild that fault tree with the known values into a fault tree that's built similar to the functional fault tree, but we call that the fault tree analysis. At the end of the day, you make a comparison to showing that your FTA meets or exceed your FFT levels. And in our specific instance, you can create a baseline with the FRA Rail and Incident Report database. The last big component of the risk assessment is the hazard log. This hazard log is a living document whose ultimate goal is to show traceability between the identified hazards and how they're resolved. So early on, if you remember the previous slide, we start out with a defined system requirements document, and that gets distilled into a preliminary hazard analysis, your PHA. Well, from the PHA borns your first entries within your hazard log. So again, this hazard log is a living document. Every design process that is undertaken gets tracked within this hazard log. In our specific case, we had everything logged in from electromagnetic compatibility to just sharp corners. Anything that can become a safety critical hazard will need to be recorded and reduced to acceptable with review or better. Your AREMA manual part 17-3 does a really good job of explaining the requirements and objectives of a hazard log. As a result of the safety process, we had to make a few minor tweaks to our original design. And the safety process also confirmed for us that some of the features we were adding initially have become a very critical piece of our safety case. So the first thing that we added within the design is a loitering time. The scanners were very susceptible to false alarms caused by wild animal intrusions or even pedestrian traffic. This particular area was rife with trespassers and animals alike. So we implemented a loitering time, and what that is it is a predetermined time that we will set into the controller, requiring the scanner to detect the object for that amount of time before sending an indication to our logic controller. So for example, if we set it to 10 seconds, the object has to be still for 10 seconds within that detection plane before we get an alarm. The second thing that we confirmed was that redundancy was an absolute critical piece of our safety case. Earlier on, once we realized that we had to overestimate on the software VMV side, it gave us a mean time hazardous event calculation that would have not met our functional fault tree goals if we did not employ redundant scanners. So again, this became a very critical piece of our final design. And the last thing we implemented was the self-test feature. So compared to the wire siphon system, our system is not closed loop. And what I mean by that is rather than looking for an absence of energy, it is looking for the presence of the beam that is being reflected back. We recognize that that is something that would be hard to address. So this is a mitigation that we've added to address that. So what that is every time the shutters roll up when we have a train rolling through, the scanners themselves will verify that they can at least identify the shutters. So say on a subdivision where you have 30 trains a day, that is 30 times a day that you are testing that your scanner is still able to preview your detection zone. And then lastly, we found that through our environmental testing, we had to redesign our bracketry and housing design. We have found that it was failing the sinusoidal horizontal vibration test. As of now, this slide fence is still currently running in tandem with the existing slide fence system. And that is all for my portion. So I will gladly entertain your questions at the end of this presentation, but I will hand it over to Mark for his segment.
Thank you, Paul, and hello everybody. My name is Mark Aston and I'm the Chief Technical Officer of ALB Foster Europe. I'd like to talk to you today a little bit more about the LiDAR system itself, how it works, and how we take our decades of experience of safety accredited LiDAR systems from the European environment into the FRA regulated application within US Class 1 railways and general US railways. So to give you an idea of how LiDAR works, if you look at the video in the bottom right hand corner here, you'll see a LiDAR system side by side with its visual counterpart. And you can see as people and vehicles transit across our grade crossing here, the LiDAR is picking up the boundaries of their legs, the sides of cars, and is very capable of detecting accurately where these objects are at any given time during times of specific interest to monitor obstacles, either on grade crossings or, in the case of rockfall, rocks on tracks. So the LiDAR works by scanning a very narrow beam of pencil infrared irradiation over a 100-foot arc up to 190 degrees total extent. And from this data we can very accurately measure whether an obstacle is sitting within an area of interest or a danger area within either grade crossings or, in the case of rockfall, on the track beds or within the area of the track ties, specifically that cause a risk to derailment or other damage to the train system itself. The system for rockfall is very flexible and can be used for a variety of applications of straight track, curved track, and we can even monitor not only obstacles but also the profile of embankments that may be unstable or prone to slippages. And this provides an additional functionality in many applications within Europe at the moment for monitoring old and aging cuttings and retaining wall structures, where LiDAR can help detect any unusual movement and then help guard the safety of the railway and the trains using it by detecting any slippages or blockages that may subsequently occur on the track. So how do we take what we have previously used very successfully in Europe into the United States as an application? Well, over in Europe and most of the rest of the world, we abide by standards and processes that are defined by Senelec's Safety Integrity Levels definition system. And we particularly employ SIL levels of 3 and 4 for sensor activities that tie directly into safety critical systems such as level crossings and signalling. The applications themselves differ slightly from FRA approval, but fundamentally contain the same level of information and requirements for reducing the probability of failure by careful design and planning and use and implementation of the systems themselves. What this means is we can directly take the information garnered for a SIL 3 approval. For example, our LiDARs are now being approved in Deutsche Bahn for SIL 3 grade crossing monitoring, and use that documentation, the evidence and the calculations on probability of failure, the MTBFs, the MTTFs, and the subsequent operability and availability of the system to directly support the application for an FRA PSP approval to Subpart H. The only other additional difference between European and US use for our products is the specification of environmental testing. So everything that we approve to local European standards here in Europe for environmental susceptibility to vibration, rain, weather, water ingress, aging effects, we then subsequently retest to AREMA standards for use in North America and US applications. And we've been particularly successful in redeploying our LiDAR design and technology through AREMA environmental testing standards for applicability directly into, for example, this BNSF Rockfall application. So what do we mean by the comparison of levels of safety between the SIL 3 certification process and the FRA Subpart H PSP approval process? Well, for a continuous operation use like Rockfall, which monitors 24/7, 365 days a year, we're looking at taking our existing SIL 3 accredited system, which operates with a PFD range of 10 to the minus 7, 10 to the minus 8 probability of failure of critical failure of the system, and compare it with the remote section D in the AREMA probability limits, which commensurately is about 10 to the minus 7 to 10 to the minus 9. So everything we do for SIL 3 is very easily cross-referenced and then reutilized for the compilation of a PSP that is submittable to the FRA. And I've summarized this very clearly by the little table we have here. So the SIL 3 documentation breaks down into 5 specific major sections, and although there are many appendices and deep levels of detail within these documents, they basically center around the customer requirement specification of how and why you're designing the system, how it's going to be used by the customer, and under what circumstances you are approving and using this system. The second documentation set is the hardware and requirement specification. Third set is the hazard, formal hazard for the system. The fourth set is very much the safety plan, so very applicable to the PSP process. And the systematic failure analysis, which also supports the main text and the main detail that's contained within a PSP approval process. And as you can see from the table, all of the relevant sections that we need to complete from our existing documentation under SIL 3 are directly relevant to the PSP process. So it is but a case of cutting and pasting and then just massaging the text descriptions to comply with the requirements of Subpart H. The beauty of this interchangeability of the information is that whatever we do in Europe under SIL 3 regime can be applied to whatever requirements exist in the USA. And the beauty of it is whatever we do in the USA can then be taken back into the European environment and subsequently used for new applications of our equipment under a SIL 3 application. And a good example of this is Rockfall, where we took our standard high integrity grade crossing monitoring system and applied it to a length of track that was susceptible to rockfall. Having completed the PSP for that system, it then becomes apparent that we can use the same rockfall system within the UK and Europe wherever there is a mountainous or a hilly cutting region where there is unstable rock formations and the surface is prone to rockfall or even rock slides. And this now is becoming a very relevant application in Europe, and I will be taking all of the information, history and experience we have learned from working with our partners BNSF in Rockfall back into the European arena. So it's proof unequivocal that whatever we do in Europe under high levels of safety integrity level are applicable within the US. Whatever is applicable in the US under PSP Subpart H is equally applicable within Europe. And the incestuous nature of this complements the railway systems for both sides of the Atlantic. So I'll leave the presentation there and hand back to Paul and the moderators. Any questions you have, obviously we are now live to support the live questions and answers, and we're more than happy to support these and any questions you may have going forward after the AREMA conference. Thank you very much for your attention.